Welcome back. In this lecture, we're going to start with the first group of software architecture patterns targeted towards our system scalability. As part of this section, we will learn the most important patterns that allow us to architect and deploy a highly scalable system for every domain and use case. This will enable our business to handle billions of requests per day, process petabytes of data, and most importantly, do it in a cost-effective way in a cloud environment. So let's start with the first and probably most popular scalability pattern, which is called load balancing. We will first understand what load balancing is as a software architecture pattern and how it works, and later we will explore some techniques to apply this pattern effectively in a cloud environment. So before we jump in to the pattern itself, let's clearly describe the problem we're trying to solve with this pattern. The problem is as follows. Let's say we have a simple web application that delivers news to millions of customers. On the other hand, we have our customers that want to read or watch those news on their web browser or mobile app. However, we can't just deploy our application on a single cloud server because it cannot handle such a high volume of requests. When the incoming traffic exceeds the CPU, memory, or network capacity of a single server, it will either crash or significantly degrade its performance, a situation we want to avoid. And upgrading that server to a more powerful virtual machine will only delay this problem. So let's see how the load balancing pattern helps us take advantage of the most fundamental feature of cloud computing, which is the access to seemingly infinite number of computers. The load balancing as a pattern places a dispatcher between the source of the data or network requests to our system and the workers that process that data and send back a response. In this pattern, the dispatcher routes each request from the client to only one of the available workers. This way, if the number of clients grows, or the rate at which those clients send us requests increases, we can add more workers and spread the load among all of them. That, of course, allows us to scale our system very quickly, without the need to make any significant changes to our system. A very common use case for load balancing is balancing HTTP requests from the front end to the back end. The front end can be either a mobile app installed on the end user's devices or run as a client-side JavaScript on the user's web browsers. And the back end is a set of application instances we run on the cloud infrastructure. Those application instances typically run as identical copies of the same application on separate physical or virtual machines. This way, instead of the clients sending requests from the front end directly to our backend servers, the requests all go to the load balancing dispatcher. And this dispatcher routes each request to one of the application instances. Similarly, if we have a multi-service architecture, such as an N-tier architecture or microservices architecture, we can deploy each service as a group of identical application instances. And all the communication to that group of instances will also be through this dispatcher. This way, we can scale each service completely independently, depending on the traffic and the workload of that service. For example, if Service 1 and Service 2 get a lot of requests, we can scale them up and place more workers behind their load balancing dispatchers. But if Service 3 doesn't get that much traffic, then we can scale it down, which will help us save money. So now that we understand the fundamentals of load balancing as a pattern, as well as some of its use cases, let's talk about two general techniques we can implement this pattern. The first one is by using a cloud load balancing service. This is a special cloud managed service whose entire purpose is to accept a high load of network requests and route them to our backend servers. The implementation details of the cloud load balancing service are hidden from us and are considered proprietary technology. Internally, they may start with a single load balancer instance that takes all the incoming requests from the client, and based on a configurable algorithm, routes those requests to a group of our servers. However, if we deploy our service instances in different isolation zones, then the load balancing service may also run as multiple instances, one in each zone. And as the traffic to our system grows, that cloud load balancing service may scale itself up and run as a group of load balancer instances. Additionally, each load balancer instance is monitored and is automatically restarted if something happens to it. This way, we don't end up in a situation where the load balancer itself becomes a single point of failure or performance bottleneck. Now, we can use the cloud load balancing service to route requests from external clients to our backend servers, but we can also use it between different services internally, just like we saw before. The second way to implement the load balancing pattern is using a message broker or a distributed message queue. Using the message broker, we can have one or multiple publishers sending messages to the message broker. And on the receiving end, we can have a group of consumer workers that read those messages. Similarly to the load balancer, depending on the volume of messages, we can scale those consumer instances up and down as we need to, so we can keep up with the rate of incoming messages. It's important to note that the main purpose of a message broker is not load balancing, but in the right use case, it can do a very good job at balancing a high load of messages to a particular service. And that right use case is when the communication between the publisher and the consumer service is one directional and asynchronous, meaning that the publisher doesn't need to or expect to get any response from the consumer after the message has been published. It's also worth noting that message brokers should only be used internally between services, while a load balancer is perfectly suited for taking requests from external services. And just like in the case of a cloud load balancing service, most modern message broker solutions are implemented as distributed systems that use replication, redundancy, and run as a group of instances. This way, the message broker is scalable on its own, and transient failures within the message broker do not impact our system. So now that we talked about the two general ways we can implement load balancing, let's talk more in depth about a few software design and architecture considerations specifically for using a cloud load balancer. The first consideration or decision we need to make is the algorithm the load balancer uses to route each incoming request to a given worker. This routing algorithm heavily depends on the design of the backend we're routing traffic to. So let's discuss a few of the most popular algorithms and how they're tied to the design of the target application. The first and simplest algorithm is called round robin. When we use the round robin algorithm, the load balancer is routing each incoming request sequentially to the next worker instance. This algorithm is very simple and is usually the default for every load balancer implementation. However, this algorithm works well only under the assumption that our application is stateless. In other words, the assumption is that each request from a client can be handled in isolation by any one of the target application servers. However, this isn't always possible, and in many cases, we need to maintain an active session between a particular client and the server it's communicating with. A classic example of such a scenario is if after authenticating a user, we keep the user's credentials on the server side to make every subsequent request faster. Now, if we use the round-robin algorithm to route requests to such an application, the client would have to re-authenticate every time for every single request. Similarly, If a client is uploading a very large file to our servers, which is broken down into multiple requests, we want to make sure that all those requests are going to the same server. And here again, if we use the round robin algorithm, our system will just not work. In those cases, we can use a different algorithm, which is called sticky session or session affinity. Using this algorithm, the load balancer tries its best to send traffic from a given client to the same server, as long as that server is healthy. This can be achieved by placing a cookie on the client's device, which will be sent with every request to the load balancer. Another way to do this is simply using the client's IP address as the identifying attribute in each request. From that point on, every request that comes from that particular client can be tracked and routed to the same server for the duration of the session. However, this algorithm works great only for relatively short sessions. But if one particular server gets stuck with too many long sessions, then it will have a disproportionately larger number of requests to handle. So for those situations, there's another algorithm which is called least connection. Using this algorithm, the load balancer will route new requests to servers that have the least number of already established connections open. The least connections algorithm is particularly useful for tasks associated with long-term connections, such as in the case of SQL, LDAP, and other similar scenarios. Now let's talk about another cloud computing feature that typically goes hand in hand with load balancing. That feature is called autoscaling. Typically, every cloud computing instance, such as a physical or virtual machine, runs a few background processes called agents. Those agents collect data about the network traffic, memory consumption, or CPU utilization on each host. Using this real-time data collected from each server, we can define auto-scaling policies to increase or decrease the number of servers dynamically based on those metrics. Now, additionally, all cloud vendors allow us to tie those auto-scaling policies to the load balancing service, so it is always aware of the size and addresses of the backend servers at any given moment. This powerful combination between dynamic resizing and load balancing gives us the ability to automatically scale our system up when the traffic and demand is high, and save costs by scaling it down when the traffic to our system is low. So now that we learned how the load balancing pattern can be used in a cloud environment to both scale our services and save costs, let's quickly summarize what we learned so far. In this lecture, we'll learn about one of the most widely used software architecture patterns in cloud computing, which is called load balancing. We first had a general overview of the pattern, where the most important feature was the dispatching of every request from a sender to only one worker in our system. After that, we talked about the two ways we can implement this pattern, which were the cloud load balancing service and a message broker. Later, we talked about some strategies and algorithms for intelligent routing of requests to our workers, based on the statelessness or the statefulness of our application, as well as based on the duration of the connection between the client and our service. And finally, we talked about the powerful combination between load balancing and auto-scaling, which allows us to dynamically resize our backend service. I'll see you guys soon in the next lecture.